Hello, everybody. So we're looking at section 2.1, starting off with chapter 2 now, matrix operations. Okay, so matrix operations work a lot like vector operations, mostly because matrices are built on vectors. Okay, so we've talked before about using the columns of a matrix A interchangeably with the vectors. You know, we've done several examples with that, used our augmented matrix in place of our vector equations, things like that. So matrices are built from vectors, so we can do a lot of the same operations, or the same operations occur the way we'd expect. So, for example, we can add matrices. So let's say A plus B, okay, where A is going to be the matrix 2, 1, negative 1, with 3, 2, 6. My matrix B will be negative 2, 1, 1, and then 14, 6, negative 3. Okay, so much like vectors, you simply add the coordinates component-wise. You add the matching spots, the corresponding locations. So 2 plus negative 2 is 0. 1 and 1 makes 2. Negative 1 and 1 makes 0. Bottom row then, 3 and 14 is 17. 2 and 6 makes 8. And 6 minus 3 is 3. So there's my matrix A plus B. Okay, now notice I had to have something in each corresponding location to add them. So added matrices must have the same dimensions. Okay, that is, both m and n in an m by n matrix must be the same in order to add matrices. Okay, so you simply add the locations. Okay, the next thing we also did for vectors is multiply by a scalar. So if I'm going to multiply by a scalar, try to clean up that image just a little bit for you. Sorry about that. I'm going to multiply by a scalar 3 here, use the same matrix A. Again, I multiply, I write it down twice. I multiply simply the individual pieces by my scalar, in this case 3. So 2 times 3 is 6, 3 times 1 is 3, 3 times negative 1 is negative 3, 3 times 3 is 9, 3 times 2 is 6, and 6 times 3 is 18. Okay, so 3 times A then is that. So notice we don't care what size the matrix is in order to multiply by a scalar. We can do that with any scalar. Okay, I just chose 3 there as an arbitrary example. Okay. So then the next thing we looked at, when we had vectors, we didn't really multiply vectors. Okay. But we can multiply matrices. Okay. If you think about it, we didn't multiply 2 vectors by each other, but we did multiply a vector times a matrix, right? We did A times X. Okay, where X was a vector. And in order to do A times X, so in this case, let's use that same matrix we were using. I had to have my vector X have as many entries as I did columns in my matrix A, because I go across the row and down the column there in the second entry. So I had to have this matching up. So ultimately, this is a 2 by 3 matrix. It has 2 rows and 3 columns. And a column vector here with 3 entries is simply a 3 by 1 matrix. So in order to multiply, I had to have these middle numbers, the 3's, match up. I had to have as many columns in the first one as I did rows in the second one. And so we can extend that definition to matrices, okay, to a full matrix. So in this case, if I'm going to have A times B, again, let me, for the sake of an example, use those same 2 that I started with before. Okay, as I look at trying to multiply these 2 ABs that I had, if I go across the row and down the column, I have 3 columns in the first one, but only 2 rows in the second one. So this is a 2 by 3, but this is also a 2 by 3. And so notice those middle numbers there, the columns of the first and the rows of the second, do not match up. So I cannot multiply those 2 matrices, A and B. Okay, I cannot multiply those. So I need something of a different size. Okay, so let's make a matrix C. Okay, my matrix C is going to be a 2 by 2 matrix. It's going to have negative 1, 3, 2, and 4. Okay, Now if I go to multiply A times C, I have 2, 3, 1, 2, negative 1, 6. I have negative 1, 3, 2, and 4. Okay, so I can multiply these to find AC. So I'm going across the row and down the column. So 2 times negative 1. Sorry, I wrote the wrong size matrix there. I want to make a 3 by 2 matrix. My apologies. That will not work at all in the way I have written it. So let's go with that. There we go. That fixes our problem. But again, then I'm going to go across the row and down the column. So 2 times negative 1 is negative 2. 2 times 2 is a positive 2. So add those together, you get 0. And then 1 times negative 1 is negative 1. So negative 1, that's the first row and the first column. Okay, if I go to the first row and the second column, that's going to be 2 times 3 is 6. 1 times 4 is 4. So 4 plus 6 is 10. Now 1 times negative 1 is negative 1. So 10 minus 1 is 9. Then I go to the second row. 3 times negative 1 is the negative 3. 2 times 2 is 4. And 6 times 1 is 6. So negative 3, 4, and 6 is going to make a positive 7. And I'm going to have 9, 8, and 6. 9, 8, and 6. 9, 8, 17. 6 makes 23. So AC then is that matrix. Okay. So notice I took a 2 by 3 matrix here and a 3 by 2 matrix here. The 3's in the middle had to match up in order to multiply, but the result was a product that was 2 by 2, which are the outer ones here. Okay. So those have to match up, but your dimensions of your product are going to match up to those other dimensions there. Okay. So you have that flexibility. Okay, or relative inflexibility, really, for matrix multiplication. You need a very specific set of circumstances in order to multiply a matrix. And it builds on that same thing that we did when we multiplied vectors and solved for solution sets of vectors. Okay, it builds on those same properties. Okay. Now, we also want to look at here, what if I look at C times A? Okay, well, you're thinking about multiplication. Well, we know that, for example, 2 times 3 is 6, but 3 times 2 is also 6. Well, we want to make sure the same thing works for a matrix. Okay, so if I take a look at C times A, so here's my matrix C, negative 1, 3, 2, 4, 1, 1. And then my matrix A, 2, 3, 1, 2, negative 1, 6. Okay, I'm going across and down, across and down, and across and down. So you can already see that this is a 3 by 2 matrix. This one here is a 2 by 3 matrix. So my matrix CA is actually going to be a 3 by 3 matrix. And certainly a 3 by 3 matrix does not equal a 2 by 2 matrix. So notice it is very important for matrix multiplication to notice that just because CA and AC are the case, they are unlikely to equal each other. Now, in some cases, they could equal each other by coincidence, but in general, commutative matrices do not, matrix multiplication does not commute, is what I want to say. It is not commutative, okay? So there's no guarantee of that. Now, as a consequence of that idea, if I do have that AB is equal to AC, I cannot say that B is equal to C. Okay, that does not give me that idea. Okay, another consequence here is I could have free variables involved. So if I have that AB is equal to 0, that does not guarantee me that A equals 0 or B equals 0. Okay, not a guarantee at all in matrix multiplication. Okay. Also, one more definition here. If we have a to the k power, okay, that simply means what we would expect it to mean. So we can do powers in the way we would expect. Okay, and we do that k times. Okay, k copies of a for the k power. So we do have powers in the way we'd expect because these matrices are the same. When there are different matrices here, we could not use that commutative idea that we use to represent exponents. Okay, so be very cautious in that in those ideas. Okay. Okay, we have some additional properties for matrix multiplication. So while it's not, or I'm sorry, not for matrix multiplication, for matrix operations. So while it's not commutative in multiplication, it is commutative for addition. Okay, so if you have a plus b, that's equal to b plus a. Okay, for addition, it's associative. So if I have a plus b plus c, I can rearrange the parentheses accordingly and do a plus b plus c. And third, if I have a plus 0, that's equal to a. Fourth, if I have a scalar multiple, again, these are built on vectors, so a lot of the operations work the same way as vectors. Okay. For addition, it's exactly like vectors because ultimately we're just sticking a bunch of vector operations next to each other. Okay. It's also distributive for the scalars, so I can do r times a plus s times a if I have two different scalars added. And then lastly, it's associative for the scalars, so r times sa is equal to rs times a. Okay, so we have those properties for addition, where we don't have a lot of those properties for multiplication. Okay. Now, similar to a problem we did at the end of section 1.9, if I have a transformation ax and another transformation, which we'll call s, that is represented by a bx, I can actually find the transformation of the two together. So t composed with s of x by multiplying the matrices. Okay, so I can do AB times x to find that composition matrix. Okay, now that we know how to multiply matrices, that gives us an additional tool to work on with linear transformations. Okay. So we also want to notice when I'm multiplying matrices, okay, so if I've got A is equal to following matrix 2, 3, 1, negative 5, and B 4, 1, 3, negative 2 in the second column, and 6, 3 in the third column. When I am multiplying this matrix, these matrices, so if I'm looking for AB, ultimately what I am doing, I'm going to label my columns here in both of these cases. So A1, A2, and A3, and B1, B2, and B3. Ultimately what I'm doing is I'm multiplying this spot, I'm multiplying this column by this row. Okay? So if I look at this, I'm multiplying the matrix A, 2, 3, 1, 5, negative 5, times the column vector 4, 1. Okay, and that's going to give me a column vector. So I'm going to put an outer matrix here because each one of these products, okay, and I'll write this one as A, B2, gives me my next column in my multiplication vector. Okay, so if I'm just looking for a specific column, I can just take the column from the second factor and multiply it by the original matrix. Okay, so notice this is A, B1. Okay, so I actually didn't use just the columns of A, A1, and A2. I'm using the whole matrix here. This gives me a column. When I multiply this, I get a two-dimensional column. Okay, so this gives me 3 columns of my matrix because this is a 2 by 2. This is a 2 by 3. So it makes sense then that the product, because the middle numbers are both 2, the product is going to be a 2 by 3 matrix as well. Okay, because the outer numbers are 2 and 3. Okay. Now, many times you have products that are undefined. We showed one earlier, but I just want to show another one here to reinforce. So not all products are defined. So let's take one here. Okay. If I go across the row 2 and 3 and down the column, I run out of places in the rows before the column. So if this is my matrix A and this is my matrix B, AB is undefined. So a good many matrix multiplications will be undefined. Okay. No reason to expect that just because it says to multiply it that it has to be defined. There are lots of them where it will be undefined. Okay. Now we have a couple more names for matrices and a couple more ideas. So if I have an identity matrix, let's call this identity matrix I3. We talked about it in the last section. That means I have the identity vectors, or the ones on the main diagonal. Okay, and we'll see why it's called the identity. So if I take my matrix A from above here, so 2, 3, 1, -5. I'm sorry. I put it I3, so I don't want to use my matrix A. Let me get a new matrix A here. My apologies. So 1, 2, -1, 0, 3, -4, and then 1, 1, 1 in the bottom row. So if I do A times I3, okay, when I multiply, I am multiplying my matrix 1, 2, -1, 0, 3, -4, 1, 1, 1. And I'm multiplying that by ones on the diagonal with zeros everywhere else. Okay, so I go across and down, so I get 1 times 1 and then zeros. Okay, then I go to the next column. I get 1 times 0, 2 times 1, so I get 2. 1, 0, 0, and then 1 times -1 is a -1. Okay, and so the same thing's going to happen all the way through here, where I just get a repeat. So if you multiply by the identity, that's like multiplying by 1. So in matrix multiplication, these identity vectors, I3 for a three-dimensional, I2, right, they're square. These identity vectors generate the exact same matrix you started with, exactly like multiplying by 1. Okay, now that's not necessarily the same thing if you add it, right? So if I have A plus I3, okay, then I am adding 1 at each of these points on the diagonal. But notice that the points off the diagonal are not going to change. Okay, so you get a very different result from addition than you might think, based on the fact that it's a identity 1. So it just adds 1 to those diagonal point coordinates because I have zeros everywhere else. Okay, so that's multiplying and adding by the identity. Now we could also multiply by a scalar in there. Maybe I do A times 3 copies of I3. Well, ultimately, the multiplying by I is just going to give me the same matrix. So I'm multiplying by 3. So A times 3 I3 will multiply all of my coordinates by 3. So 3, 6, -3. 0 times 3 is 0. 3 times 3 is 9. -4 times 3 is 12. And then I would get all 3's on the bottom row. And a similar thing then if I'm adding. I'm only adding to that diagonal because those are my only non-zero points in the identity matrix. Okay, we're going to go to the next page now. Okay, so we want to touch on a few properties of matrix multiplication. We made a list for matrix addition, so we're going to make a similar list here for multiplication. So although we're not commutative, we do have an associative property. If I have A times BC, that's going to give me the same thing as doing AB first and then multiplying by C. Okay. Now, we do have distribution, but we actually have two different distributive laws. So if I have A times B plus C, I can distribute those on the left and get AB plus AC. But if I rearrange them where I put B plus C on the left and then A on the right, that gives me a different product. But that's going to be B times A plus B times C. I'm sorry, C times A. I wrote the wrong thing down. C times A. Okay, so notice we flipped both of those around when we flipped these around. But there's no reason to expect these to be equal to each other. So notice that law 2 does not equal law 3 or rule 3. Okay, we should not expect that to happen. Okay, we can move our scalars around as we need to. So R times AB is going to be the same thing as A times RB. So if you want to multiply by matrix B first, or if you prefer, you can multiply by matrix A and then multiply that by B. You can get all of those together. And then we just talked about we have an identity property. So if I have IM times A, where I is the appropriate sized identity, that is the same thing as A. Or I can flip them around if it's the identity. I can multiply by the identity on either side. Okay. Now we have one more term here when we're talking about matrices, and then I have a few more example problems. And that is the transpose. So we're talking about the transpose of a matrix. That is where we flip the rows and columns, okay? So the transpose switches rows and columns. So if I have a matrix here, 1, 2, 3, 4, negative 1, 1, and I want to take the transpose of this matrix. So we represent the transpose with that small capital T as a subscript. Okay, so I'm looking for A transpose, and that's my matrix A. Well, the transpose of it then is going to switch the rows and columns. So right now this is a 3-row by 2-column matrix. So the transpose is going to be 2 rows by 3 columns. So I take this first column, and this first column becomes my first row. So 1, 3, negative 1. And then the same thing in the second column, 2, 4, 1. Okay? So we just switch the rows and columns. Okay? Fairly easy to compute a transpose. Let's do one more just to make sure we're on the same page. We'll go with all ones across the top row here, and then negative 1, 2, 3, negative 4. Okay? So again, we're going to switch the rows and columns. So we're taking the transpose of this. So the transpose is going to take this row and make it into a column. So that first row of all ones becomes a column of all ones. And that second row, negative 1, 2, 3, and negative 4, becomes a column as well. Okay? Now we have a few properties for transposes. If I take the transpose of the transpose, I just get back where I started. So if I switch the rows and columns and then switch them back, I'm right back where I began. Okay? If I add transposes, I know that's a weird phrasing, that is the same thing as adding the matrices first and then taking the transpose. Okay, it makes sense because they are both transposed, so I'm adding the same corresponding positions. It doesn't matter if I switch the positions first and then add, or if I add first and then switch the positions. Okay, we also have scalar multiplication for transposes. So if I do RA and then transpose it, that gives me the same thing as doing R times A transpose. Same idea as the addition. If I multiply first and then switch the positions, or if I switch the positions and then multiply, I get the same result. Okay. And then maybe the most interesting property is that if I have AB, a product that is transposed, the resulting product is the transposes of the reverse order. So I have AB quantity transpose. That's the same thing as B transpose A transpose. Okay, or if I switch it around, I could have BA transpose. That would be the same thing as A transpose B transpose. Okay, think of it in either way, whether you use A, B in that order. And you can use any letters, of course. A and B are just arbitrary choices to write the laws down. But we can go in any order. But when I switch it with the transpose, that's going to give me that result. Okay, so transpose switches the rows and the columns. Okay. All right, so I promised some example problems. So let's look at some example problems that we could do here with matrices. Okay, first up, I'm going to have 2 matrices that I'm going to multiply. And you think, well, we've done examples of that, but we're going to complicate things just a little bit. So I have 2, 3, negative 1, and 1. My matrix B then is going to be 1, negative 3, 9, and K. Okay, so K is unknown. And it's going to tell me that AB is equal to BA. So remember, that's not a regular property. But what we're telling you is this is a property here. Okay, and so what value or values must K have? Okay, so if this is to work, I'm going to need a very specific value for K, maybe more than one, but I'm going to need some specific value for K. K can't just be anything because we know that this commutative property is not normal. Okay, it's very unusual for multiplying matrices. So let's compute our 2 products. So AB, okay, I'm going to write out my matrices. You could probably use some fewer steps than I'm writing out here, but just to give you an idea, I want to make sure I'm careful and we don't skip over any steps. So I have 2 by 2 matrices being multiplied by each other, so the product is going to be 2 by 2. So I get 2 times 1 is 2. 3 times negative 3 is negative 9. So I add those together, I get negative 7. Okay, so that was first row, first column. So I'll go second row, first column. That's 1 times a negative 1 is negative 1. Times 1 times negative 3 is negative 3. So I add those together, I get negative 4. Okay. Let's go first row, second column now. That's 2 times 9 is 18. And 3 times K is 3K. So that's going to be 18 plus 3K. Okay. Second row, second column, I've got -9 plus k. -9 plus k. Okay, so there's my a times b. Now let's compare that with b times a. So again, we're switching the order around. So I've got 1, 9, -3k. Then my matrix A is 2, 3, -1, 1. Right? And so we go across the rows and down the columns again. So 2 times 1 is 2, times 1 times a -9 is a -7. Second row, first column, I've got -6 minus k. Second row, or first row, second column, 3 times 1 is 3, 9 times 1 is 12. Second row, second column, I've got -9 plus k. Okay, and now I know in order for matrices to equal each other that the components all have to equal. Okay, so -7 and -7 are equal. We're good on that. In the lower right, -9 plus k and -9 plus k, those are also equal. So we're good there. So that leaves me with two equations here. I've got 18 plus 3k is equal to 12. Okay, that is my upper right equation. And then in the lower left, I have that -6 minus k is equal to -4. Okay, so let's solve these relatively simple equations for k. So I'm going to take the -18 to the other side. So I get 3k is equal to -6, which means that k is equal to -2. On this one, I bring this over, so I'm going to get -k is equal to -4 plus 6. That's 2. So k is equal to -2. So these k's here that I got for those equations are the same, and that in fact tells me what value of k I must have in order for this equation, this unusual setup of commutativity, in order to be true for these matrices. If I have any other value of k, then these two coordinates here, these lower left and upper right locations, will not line up, and I will not have equality. Okay, so be very careful to make sure you get that result. Okay, you want to get the coordinates or the components to match up in the corresponding locations. Okay, another thing you might be asked is, let's say I have a matrix A, -3, 1, 2, 4. We'll call that matrix A. And it's multiplied by a matrix B to get the zero matrix. Okay, so I have AB is equal to the zero matrix. Again, 2 by 2 here, 2 by 2 here, and a 2 by 2 result. Okay, so pay attention to the dimensions, make sure you take care of those. So I don't know what the components of B are. Now, knowing what we know about linear equations and linear systems, I know that one choice is certainly to make B equal 0, the zero matrix. Okay, we have the trivial solution. Okay, so we do have the trivial solution, but most often we're looking for a situation where I don't have that trivial solution. Okay, that's where it gets interesting for us. Okay, or perhaps that's the only solution I have, but that's what we want to look at. Okay, so as I look at this, what I'm asked to do here is I'm asked to find what would I multiply this by, row by column, row by column. Okay, what would I multiply this by to get zeros here? Okay, well, if I think about what that is, that's A times a vector x is equal 0. I'm being asked to solve the homogeneous system. Okay, so as I look at this, these are linearly independent. And so if they are independent, then the only vector is going to be the trivial solution. Okay, so for this matrix A, I have only the trivial solution. So let's try a different matrix A. Okay, this matrix is going to be 4, -12, -1, and 3. Okay, now as I look at my columns of matrix A here, matrix A has they are a linear combination. So if I look at second column, the second column is 3 times, -3 times the first column. So notice that A1, -3A1 is equal to A2. So those are a linear combination, which means that this is going to row reduce, right? You go in and row reduce this, it's not going to turn into the identity matrix. Okay, so I'm going to get 1, -3, 0, and 0 when I row reduce that. Okay, which again matches up with what we see down below here, that this is -3 times. So there's that -3 again. Okay, so that means that the appropriate vector is going to have x1 equal to 3x2. And x2 then is a free variable. X1 is equal to 3x2. So then one possible vector, so one possible B1 would be 3, 1. Okay, because x1 is 1, which makes x2, I'm sorry, x2 is 1, which makes x1 3, because it's 3 times 1. Then if I need unique vectors, maybe I don't want the same vector each time, we can just multiply those results by 2. So the matrix B that will work here, if I do A times B, so my A is 4, -12, -1, and 3, and my B is 3, 1, 6, 2. Those will multiply to the 0 matrix, because I'm going to have 4 times 3 is 12. -12 times 1 is -12. That's 0. 4 times 6 is 24. -24 is 0. -3 and 3 is 0. And then second row, second column, -6 and +6 is 0. Now, you could do lots of different matrices here. You could do 3, 1 and 9, 3. Anything that works as a combination or a multiple of this 3, 1. It would also work with just 3, 1 and 3, 1. Many times we kind of find that type of matrix to be a little bit boring. Okay, so ultimately we are solving the system, the augmented matrix of A augmented with the column I am looking for, AB1. Okay, find AB. So we're solving that augmented system. Okay, and so we can use that to our advantage. Okay, so remember to pay attention to the dimensions when you're talking about multiplication and addition with matrices. Okay, very important. Remember that ultimately we are just doing the column multiplication like we did in chapter 1 when we're talking about multiplying matrices. Okay. Okay, one more example that I want to do here is a specific type of matrix which we call upper triangular. Okay, so when I say a matrix is upper triangular, we talked about triangular matrices in chapter 1, so we should be somewhat familiar with that terminology. So let's call this matrix S. Let's make it a fairly large matrix. So it's going to be 3, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 3. Then all zeros on the bottom row. So notice I have this upper triangular pattern here. I have a lot of zeros, so that's pretty nice. I'm going to make multiplying fairly easy. And so these 3's here are not lined up on the diagonal. They're just off the diagonal. So if I go to do S squared, okay, it's going to take me a second to write down this matrix. All right, I got to write it down twice also because we're doing S squared. Okay, once you see the pattern here, you won't have to write it down every time. You can identify what's going to happen here. So S squared is going to be that times a copy of itself. Okay, so when I go to multiply these, I'm going to have 0 times 0, and I get zeros all the way down because I've got zeros all the way down that first column. Okay, so the first spot is 0. Okay, I go to the second row now. I've got zeros all the way down. 0, 0, 0, 0, 0, 0. Because I got 0 times 3, 3 times 0, 0 times 0, 0 times 0, 0 times 0. So I get 0 again. Okay, I go to the third column. I've got 0 times 0, but then I get a 3 times a 3. So I've got a 9. And then I get 2 more zeros. Okay, because third column, I'm going to not have those matching. I'm going to get all zeros. Fifth column, all zeros as well. Okay. Second row now, all zeros. Second column then, all zeros again. Third column, all zeros because it's 0 times 0, 0 times 0, 0 times 0. Fourth column now, that's where it's going to overlap. 0, 0, 0, and 3. So I get a 9 in that next position. Okay, and so you can see what's going to happen in the third row is I'm going to get a 9 in that last position, and then I'm going to run out of 9s, so to speak. So when I multiplied this, what I did was I wound up squaring the 3 to get 9, and it shifted it out one position on the diagonal. So if I went to s cubed, the same thing is going to happen. So I'm going to take those 9s, but now instead of being in that sort of third diagonal position, they're going to get multiplied by 3 again. So I'm going to get 27, but it's going to shift it out another position. Okay, and then I'll have all zeros there below it. Notice I'm multiplying 5 by 5, so my result is a 5 by 5 as well. Okay, so then s to the fourth would put 81 here in the upper corner. And then when I went to s to the fifth, I would actually push it totally off, and s to the fifth would just be a matrix of all zeros. It would be the 5 by 5 zero matrix. Okay. Now notice when I am multiplying, when I'm talking about powers of matrices, I only have powers for square matrices. Okay. So s to the k power is defined only for square matrices. Okay, because if I don't have a square matrix, if I have s times s and they're the same size that aren't square, so if I have 3 times 2 and a 3 by 2 and a 3 by 2, notice those middle numbers, the columns of the first and the rows of the second, do not match up. So I don't have that property in order to do that multiplication. Okay, that should cover everything, get you started on matrix operations, section 2.1. Okay, if you think about in multiplication, we have an inverse, right? We're very familiar with multiplying by the reciprocal. So for example, 3 times a third is 1. Well, in matrices, we're going to also have an inverse. Okay, but instead of being 1, right, our matrix is the identity. Okay, so section 2.2 is going to deal with the inverse of a matrix and lead us to a very important invertible matrix theorem that is in many ways the basis for much of the rest of our chapters. We just keep adding to our invertible matrix theorem throughout the rest of the term. Okay, if you have any questions, please get in touch with me. Contact me by email or stop by office hours, whatever it might be that I can help you. Be mindful of those quizzes and checks for understanding. Make sure you are completing all the waypoints along the way. Make sure you're staying up to date with the homework assignments. There's a lot of points you can earn from those assignments. All right, and I will talk to you in the video for 2.2, or I'll see you soon online at that point. Talk to you soon.